Okay, so it is 3:30. We're going to get started. This is a problem about, quote, real life, end quote. So I have these 4 peppers on the counter, and my wife says to me, please cut up the red peppers and green peppers. Please cut them up. You probably know which peppers they are talking about, but the problem is you need to answer in math notation. So you need to tell me, do I mean U or do I mean upside down U? So hopefully you can see that. Maybe I'll zoom in a bit. You need to know which symbol is which. And you were told about these symbols last class. I will give you a little reminder here. I will use the Wikipedia page. So let's do the Wikipedia page. Wikipedia, intersection and union, these are the 2 things we want. Let's stay signed up. So union, there's one, and intersection, there's one. And we can, so here's the little U, that's a union, there's a nice picture, and here is the kind of definition you were given last class. So if you have A union B, this curly bracket means set, so we're talking about a set of things, and this one is the set of things that are in A, this funny E-shaped means in, so X, where X is in A or X is in B, that's union. And intersection, very similar looking thing, except it is with an and. Oh boy. It's with an and, okay. So this upside down U, X is in A, that's how you read that out loud, and X is in B. So one of them is an or, one of them is an and my question to you is, we're talking about these peppers. Which one are we talking about? So my wife says to me, chop up all the red peppers and green peppers. Which one are we talking about? And I'll write down the definitions for you. That's what we're going to be talking about today. But now you know all the stuff for this problem. You know what we did last time. What is the answer? So can you express what we want to do with these peppers in terms of either a union or an intersection? I'll give you like 2 minutes to do that. I'll write down those definitions, and then we will come back together and go from there, okay? So go ahead and work on those. Okay, there's like 10 seconds left. Put in your final guess on what it is. Even if you don't know, you must guess now, because that's what we're doing. Mathematize. Okay. 91 people answered. What did people say? Count. How many people said which? 68 people said the union. 23 people said the intersection. So most people are on union. Here is a thing I want you guys to puzzle about. In this question, it said and. why did everybody pick union, where union is the or? So here were the two definitions, if I can find it. Union is or. So the question said red peppers and green peppers, and you guys all picked the one with the or. And that's because you guys are right. Let me show the right answer. So you're absolutely right. Almost everyone got it, 74 to 26. Even though the question has no ors in it, and it has an and, you guys correctly figured out the right answer is the one with an or. And I find this thing very confusing. How could the question not have an or, but the answer is an or? Not only that, imagine if somebody had said, pick up all the red peppers or green peppers. Then you would think they mean like one or the other. Like you wouldn't think they mean either of these things. So what is the point of all this? Sometimes in probability we have these special words like and the and in real life and the and in probability are different words. So you guys have figured this out. I think maybe most people, maybe the thing that was helpful, I tried to scroll by it really quick so you wouldn't notice, but is the pictures. How many people like this kind of picture and that's how they visualize what's going on? These pictures are really helpful to see what's going on. So a union is everything that's in this one or everything that's in this one. It includes both. The or is kind of like the condition of being in one or the other. And that's all the peppers. That's what we wanted. So if you saw that picture and you're like, of course, the red peppers and the green peppers, no problem. Then maybe that's how you did it. Whereas intersection is only the things that are in between. So here's the picture. So if I did the intersection, that would be only that middle pepper, pepper P2, that was both red and green. So you guys, I think, have figured this out, or at least lots of people got it right. But there are lots of other special math words that are hard to figure out. And so I wanted to spend a little bit of time working with these to make sure we get them right. And so I'm going to make a little table here with special math words in probability. And that's what we're sort of doing today. Special math words. Special, and I'm going to call them special probability words, actually. Okay, and two of them, and or, are already on our list. Oh boy, this page already has a bunch of stuff on it. Let's make a new page. Okay, special probability words. And so two of them are and or, but even more fundamental than that, I think, is a word that we talked about last class, and is something called the sample space. The sample space. So this is going to be my list of words. And I think the sample space is the most important word of all of the stuff we're going to do in these first few weeks, because all of our probability is based on the sample space. And you have this nice handout here with the sample space for rolling two dice. So maybe let's include an example in our column, our two dice example. And the sample space is literally all these different things that could happen when you roll two dice. So, and we draw them with big curly brackets. So I'm going to draw them like this. Big curly bracket to include everything. And it's 1, 1, 1, 2, all the way up to 1, 6. Then 2, 1, 2, 2, all the way up to 2, 6. And so on. All the way up to 6, 1, 6, 2, all the way up to 6, 6. So there's 36 things in this sample space. And the thing you need to know is sample space means this kind of special collection of things, and it comes with a rule for doing probability. In our case, the rule for doing probability is the equally likely rule. So this comes with the equally likely rule. So the probability of something is going to be the number of things in the something. Let's call them elements in A divided by, in this case, 36, but in general, it's the size of S. So let's call this thing S, and we'll say the number of things in S. I'll write it like this. The number, and then these lines, and you count up the number of things in S. So you guys were using that rule last time without even saying it, when we calculated that the probability of rolling a 3 was 2 out of 36. We said there's 2 ways to roll a 3 in our sample space. The sample space has 36 things in total, so the probability is 2 out of 36. Very technically, this thing is the sample space. If you have the sample space and this probability rule together, sometimes people call that a probability space. A probability space. So I'll put a little AKA here. That's something else you got to watch out for. Space is just math speak for thing. So this is like the probability thing. But you have to know, when we talk about these things, what it means. And it's kind of possible to do a lot of probability calculations without really thinking about the probability space. But every now and then it comes up. And to really understand what's going on, you really want to be able to think of this. And in fact, we're going to move towards something called conditional probability very soon. And in conditional probability, my feeling is if you don't understand a sample space, you're just going to get totally lost. There are going to be some weird formulas, nothing will make sense. But if you have the sample space, it's all very easy to understand. So that is the first special word, is the sample space. And in general, it can be any set. So here's my example. In general, it can be any set at all. So whenever you have random outcomes, you take all the different random outcomes that you want, you put them in a big set called S, and then anything that you want, you can make it random by just putting them in the probability space S and declaring some probability rule. Another example that was used last time was the sample space of letters from the English alphabet. So that would be like a monkey typing on a typewriter. If we think about what is the next letter they're going to type, that would be a letter A to Z. You can make S something really exotic. You could say S is the set of possible universes. And then you can think about how is this hydrogen atom going to end up or not. So S really can be anything. I think it's equally good. You can think of this as like the multiverse of possibilities. That's a fun way to think about it. The multiverse of possibilities. Okay, I guess maybe this shouldn't go in the word column. This should go in the what it is column. So all possible outcomes, and it represents all possible outcomes. Okay, so there's your first special word. We're going to get to and or in 1 minute, which is the union and the intersection. The other things that you might want to do, let me get my notes here and make sure I don't miss one. Okay, there was something called a simple event. A simple event. And a simple event is just any one of these individual possibilities. So mathematically, a simple event just means one element of the set, which is the probability set. So as an example, we could have the outcome 2, 1 in S. That's the example. And in general, it's any element of the set S. Okay. So this is kind of like basic set theory you need to know. A set is just a collection of objects. In probability class, we make them the possible outcomes that we want. We call that the sample space. And a simple event just means any individual element. This is not to be confused with an event. An event. And again, the word event is not the ordinary English usage of the word event. When you say like something that happens at a certain time or something, an event is a subset of the probability space. And an example is the event we did last class, and you guys did it without talking about any of the math notation, which is the event that the sum of the dice is 3. That was the problem we started with last class. This is the event where it actually has 2 elements in it, 1, 2, 2, 1. And it's a subset of the space S. So you can kind of think about it. You can highlight, for example, the set, the parts that are in the subset. So it's some collection of the elements, not all of them, but more than one. And the thing is, being able to go from this kind of description, the sum of the dice is 3, That's like an English language description, and being able to convert that into which elements it is exactly what you need to do to be able to answer questions like what is the probability using the rule. So this is a lot of what probability is. Someone gives you something they care about in English words, and it's your job to come up with what is the probability space and what is the set they're talking about. Question over here.
Yeah, just before you got too far in the first box, the formula that you put up.
Yes.
What is that solving for? Is that like a P and a
Okay, this is great. This is, I didn't define what this means. Let me write it again a little bit neater. So this is a P, but it's written with 2 lines. Has anybody ever seen, say, an R written like this with 2 lines? It's the same kind of thing. R written like this is the real number line. And this font, where you add a line, is called Blackboard Bold. And it's for people who want to write bold things, but all they have is chalk. Of course, I have a pen, so I could probably do something better. But this bold P is the symbol for probability. And so probability is something that inputs the event and outputs a number. Maybe let's add it to the list. This is a great thing. So event, okay. And we have P, this funny symbol P. This is the probability function. And let's do it an example. Let's give this sum of dice is 3. Let's call that S3 for sum is 3. Okay, S is already taken. Let's call that A sub 3 for the sum of the dice is 3. And we know that the probability of the set A3, that's what we did last class, is 2 over 36 from last class. And this symbol means the probability of an event. Maybe even more generally, the probability is a function that inputs events and outputs numbers in 0, 1, and it has to obey certain rules. So if you like thinking in terms of functions and inputs and outputs, it's okay. If you're scared of this notation, don't do it. But it inputs subsets of S and it outputs numbers in 0, 1, and it has certain properties. But if you don't know what this notation means, don't write this down. But if you are excited by this notation, I encourage you to write it down. This is, as you take more and more probability, this kind of thing gets more and more intense. So that's the probability function. And it inputs, like you see over here, we input an event and we output a number, and we use the rule, this equally likely probability rule, over here. Okay, great question. And now I have defined the notation P for probability. Any other questions at this point? Yeah.
What if we had like an unfair die? Like, that wouldn't show in the sample space really?
Yes, this is a great point. So let me also give this a name. Let's call this thing. This specific rule is the equally likely probability rule. Equally likely rule. Okay, this one is named in simple English, and it makes perfectly good sense. And you can have a sample space with a different probability function other than the equally likely rule. We're starting out this class with the equally likely rule because it's the easiest one and it kind of makes intuitive sense. And then once you guys understand that one well, then we're going to move on to more and more complicated ones. So this rule that we're using for now is a special type of probability. In general, you'll see that you can define anything you want on the sample space as long as it obeys certain like axioms. Let's say. So P is the probability of an event, and P must obey certain rules. Must obey certain rules, and we'll tell you exactly what they are later, because for now we're going to stick to the simple example that we have. Fantastic question, and yeah. In fact, I think Gary alluded to this last time. You can do probability on sets where the sample space is infinite. And once the set is infinite, counting up things is not going to work. You're going to have infinity divided by infinity, and everything will break. So once you have infinite sets, you need to do lots more complicated ways to define the probability function. We'll get to this kind of thing eventually. So lots of exciting things you can do here. But for now, we're starting with this one. Other questions? These are wonderful. Yeah?
There's a question. What's the font they used again?
It's called Blackboard Bold. And yeah, if you type in, there's a common way to type math is something called LaTeX. And you would do /math BB. That stands for Blackboard Bold P. That's how you would make a fancy P appear on your computer or your GitHub file or whatever. Blackboard Bold. Same with R. Yeah. Of which? Of event?
Yeah.
Yes, event. Okay. Right. So an event, I gave you an example, and I think I said it in words, but let's write it down. The definition of an event is any subset of the probability space S, of the sample space S. And a subset means some collection of elements, but not necessarily the whole thing. Some of them, but not all of them. That is called an event. The fact that events are subsets is why we need all this union and intersection stuff, right? When we're going to take our probability problem, like something like the sum of the dice is 3, please calculate the probability, it's a question really about subsets, right? Subsets of the probability space. And how do we deal with subsets? That's why we need unions and intersections and all that. It turns, this is really the mathematical foundations of probability. We have these things in real life. How do we deal with it mathematically? We turn it into sets and subsets and counting and things. We're sort of taking real life stuff and turning it into set theory and working there. Other questions? Okay. Let me add, on my note here, I see that simple event has a few other aliases. Another one sometimes people use is outcome. Outcome. So sometimes people will say an outcome. Another one that I really like that is maybe less common for elementary probability theory, but later becomes more important is something I call an atom. And so just like the table is made of atoms, and that's what holds it all together, and it's kind of this big collection of atoms that are all glued together, you should think of the sample space as some big thing, and it's made of these little individual pieces, the atoms, and it's our job to figure out parts of it, how are they related? So this half of the table is some event, this half is another event, and so on. Okay. All right, next up, I think are the ones that you guys were quite good at already, is if you have the word and, what does the word and mean? And so and has a special word is a special word in probability, and you should not confuse it with and from real life. And from real life means like take all the stuff, put it together, but A and B is not the red peppers and the green peppers. A and B is always intersection. So if someone says A is an event, B is an event, I'm thinking of A and B, they mean the intersection. And let's do the definition and then I'll do an example. So A and B always means A intersection B, and that is the set of all elements E such that E is in A and E is in B. So it's always an and in terms of the conditions, right? Like if I said the red peppers and the green peppers in probability class, I mean the peppers that satisfy both being red and being green. And I think I did this earlier, but let's do it one more time. Let's call out the parts of this thing if you've never seen it before. So this curly bracket means start of a set. Start of set. This curly bracket here means end of the set. And this colon in the middle here means such that. This is a such that. Such that. So what does it say right out loud? I'm thinking of all the things E such that E is in A and E is in B. The symbol is also in. That's another good one to know. This means in. So I'm thinking of the things that are both in A and in B, and this is really good to draw a picture of what it looks like. Here's A, here's B, and we're talking about the stuff that are in both A and B. Okay. Who's very comfortable with this notation, these ins and stuff, has seen them before in high school? Okay, most people. That's good. All right, let's do a quick example here. We'll do one from your notes over here. Yes. So if E2 is the event that die 2 is even, and E6 is the event that the sum is no more than 4. So these are both events on this probability space that we talked about last class of all the dice rolls. I think they even got highlighted last time. So E2 dice number 2 shows an even number, these are like rows. So E2 is like this row, and the 4th row, and the 6th row. And E6, the sum is no more than 4, is like a little triangle in the corner over here. And if you take their intersection, it needs to be both that the first dice is even and that the sum is no more than 4. So the event E2 and E6, which it would be more proper to do it with an intersection like this. So let's see, the first dice has to be even, so it could be 2, 1, 2, 2, and I think that's it. Okay. So this was an example that got done right at the end of last class. There it is again, an intersection in our language. Okay. Similar idea for or, a or B. And once again, the or in real life is different than this or. So you got to be careful, right? If I said the red peppers or the green peppers, you would probably expect me to cut up one of them but not both. But or is always, in math, is always an or that includes everybody. So it really should be like A or B or both. That's how you might think about it. And in the picture, it's A and B, and it's all the stuff that's in both of them. So we want the red peppers or the green peppers. Mathematically is what you would say in real life as red peppers and green peppers. I know it's confusing, but that is the way it is. So A or B equals A union B is the set of E such that E is in A or E is in B. And without saying it, people also mean or both. So don't forget that, or both. Okay. I think we did an example with the peppers. Maybe that was a good example. E.g., red union G equals all the peppers. Okay, but not the yellow one. No, that one's no good. Hopefully that example is okay. All right. We're breezing through these. Any questions about and or? You might ask, why do we care about and or? And you will see as we kind of build up to harder and harder problems, a lot of times the way you solve a probability problem is you take some complicated thing and you write it in terms of ands and ors of simple things. So it's sort of ands and ors let you combine simple things to get something more complicated, and that is how you will calculate probabilities. Question here, yeah. The E2 and E6, yes. Let me do the E2 and the E6 one more time. So let me let's draw a full. Okay, so E2. I skipped some of the rows here. Let me add in the row. So 4, 1, 4, 2, all the way up to 4, 6. So this I've attempted to draw the probability space with 36 outcomes. On the handout you had last class, it really is drawn for you there. And E2 is the event that the second dice is even, or was it the event that the first dice is even? Because I've circled the one that the first dice is even. Okay, let's make. All right, let me do a slight modification. Let's call this E2 tilde is dice 1 is even, so that my example fits nicely on the board. Okay, so you could swap this whole thing. But E2 is the event of these purple rows. So E2 is a subset of the full probability space. It's got 6, 12, 18 elements in it. It covers half the probability space. It's the second row, the fourth row, and the sixth row. And that's where the first dice is even. And then the other event is the fact that the event that the sum of the dice is less than 4. That event looks something like this. It's a little triangle that looks like that. This is the event E6, both dice. Sum is less than or equal to 4. So maybe, I'll draw a cartoon, because I think I love cartoons for math. Cartoons in math are the best thing. So here is the full probability space S. Here are the event E2 tilde are these rows, and E6, the sum is no more than 4, is this kind of triangle in the corner. And what is in common between the purple and the orange is only the two things that are here and here. And those are the things 2, 1 and 2, 2. This is lovely. This is like a little flag of this question, right? Okay. This is a little cartoon. Maybe hopefully it helps you understand this thing. So what's left is 2, 1, and 2, 2. Those are the only things they have in common. What is in both the orange triangle and the purple rose? It's only the two events, 2, 1, and 2, 2. That's the only way you can roll 2 dice and have the first dice be even and the sum be less than or equal to 4. Okay. Other questions? These are very good. Okay, so that's and or. And last time, we talked about another sneaky one called disjoint. And disjoint is one you got to be careful for, because just like the other things in real life, disjoint kind of has this idea in real life, and the probability word is very specific and is not necessarily the same as in real life. Here's the first mistake you can make. Could you write A is disjoint? What does it mean for A to be disjoint? This is total nonsense. If you see somebody saying A is disjoint, like it's no good. Disjoint is something that happens between two sets, okay? So you cannot ask if one set is disjoint. What you can ask is, are these two sets disjoint? What is the relationship between them? So disjoint is never like this. In fact, it's worth writing down and crossing out. And then what you can ask is, A, B are disjoint. That makes sense. So disjoint is a property. Any two sets, they either together are disjoint or they're not. Sometimes people will use it and they'll say, oh, I have 10 sets. They're disjoint. They mean any two of them are disjoint. So it's something that happens to pairs of people. It would be tempting to say it's like being married. You need two people to be married. But the problem is in English, you can say an individual is married. So I can't think of a good English word. Maybe this is good homework. Come up with a good English word that has the same property. You can't do it for one. What is an English word that is like this? I guess a pairwise. If you can think of a cool one, let me know. Oh, I'll make a forum post, and you guys can post your favorite words in English that only apply when you have two people, and I will give the person with the coolest word, measured by upvotes, a free coffee. Okay? So I'll make a forum post, and we'll come up with some good words, like the word disjoint and probability, that it makes sense when you can ask about two. It does not make sense on its own. Okay? And married is right out, because English is weird. Okay. But what does disjoint mean? The picture is they have nothing in common. They must have nothing in common. This is the English definition, and the way you would write it mathematically is A and B are disjoint. It means that the intersection is nothing. How do you write nothing in math? You do this cool 0 with a slash. That's the empty set. So the overlap between A and B is nothing. Yeah?
Could it be only two sets or two or and more?
So almost always people mean two. If somebody gives you a list and they say they are disjoint, what they probably mean is any two of them are disjoint. So if I have 4 things and I say these sets are all disjoint, what I probably mean is if you pick any two out of these 4, there's 6 ways to pick 2, any two of them would be disjoint like this. It would be more accurate to say pairwise disjoint in that situation, but that's what we want. If you have 3 sets and the intersection is empty and they all individually overlap, I think it would be misleading to say these 3 sets are disjoint. So disjoint, only 2 at a time. Do you agree with that, Gary?
Well, to me, a disjoint is that you simply do not have any intersections between any pairs.
Any pairs. Okay, so for you, disjoint and pairwise disjoint are the same thing.
Yeah, so
Yes.
we would say mutually disjoint.
Right. Mutually is a good way to say it. Yeah.
Mutually disjoint.
Question here.
In that sheet that you gave us, was the one with the one event and the line?
The line.
And separating it, is that?
No, the line is something to do with conditional probability. And we're going to either get to that at the end of this class or at the beginning of Friday's class. Yes, this is very good. I saw there was one more question, yeah.
What about the union for disjoint?
The union, we are not making any statements about the union. So disjoint is only about do they overlap. Their union could be everything. Their union could be something really small. The only thing we're saying when we say they're disjoint is we're only talking about how much do they overlap, and we specifically mean the overlap is empty. That's it. And I'll draw the picture. I think the picture helps. So the picture for disjoint sets is like this. A is something, B is something, and they better not overlap. No overlaps between A and B. If the A and B overlap, they are not disjoint. out of all of the ones that we've done so far, this one I think is the trickiest one, and especially because if you don't have this picture of the sample space in your mind, then you will never figure out disjoint. And that is why I made a hard problem for you guys to do right now on Mathematize, figuring out a bunch of these disjoints. And they are all the sets over here. So let me open up this Mathematize problem for you and give you guys a stab at trying to do some disjoint sets, and we'll see how we do. So here it is. These are the sets. They're exactly like in the handout, E1 to E7. And the question is going to be, which of these pairs are disjoint? And there's like 4 options. And remember, I'm giving you 2 sets at a time. I wrote with to make it clear that I mean, are these 2 together? Are they disjoint or not? There was a question at the back?
I was actually going to ask about that, like, about 2 of the examples from the sheet.
Uh-huh.
Like, is conditional being, like, where the ones that are, like, odd and then the other ones?
Yeah. So why don't ask me again if it's still unclear after we do this. So hopefully we'll do it, and it'll be one of the examples. Okay, so take a few minutes to do it. If you have a question, you can put up your hand, and either myself or Gary can come around and help answer the questions, and we will reconvene in about 2 or 3 minutes, and we'll see how people are doing. Oh yeah, I have some as well, yeah. Yeah, if anybody needs a sheet, put up your hand. We have some extras here. Okay. Oh, okay.
Like your deck, they get messed up, and then you be able to.
This is a good point. So if you check the back of your sheet, you'll have lots of examples of the subspace S where you can scribble all over it and kind of do each problem. That might help you if you're drawing them out. Let me give you guys another little bit of time here, so it's not due as soon. Okay, I would like to see how people are doing. So 1 minute left, and then I'm going to really collect the answers. So try to get in your guesses in 1 minute. If you're not sure, you got to take a guess. That's okay. Take your best guess. Okay, let's take up your guesses, and we'll see which ones. Some of them maybe are easy, and some of them are hard, and we'll spend more time on those ones. Okay, so let us reveal. All right, so out of 94 people, 90 people think E4 and E5 are disjoint. 88 people think E3 and E4 together are disjoint. Notice I'm using the word and, but and is a special word. That's why I wrote with over here. So you got to be careful when somebody says this one and that one is disjoint. They mean like together they're disjoint. They're not talking about the and. You have to know based on context what they mean. So I tried to be extra crystal clear in my problem. In real life, you're going to encounter all sorts of weirdness with the word and being a mix of regular day and math and. So someone might say E3 and E4 are disjoint. That's what they mean. So let's see. We have out of 94 people, 90 and 88 people thought these two were disjoint. Only 8 and 5 people thought these were disjoint. So it looks like you guys are pretty well settled. It's a pretty good majority rule. Let's reveal the answers and see how you're doing. Everyone got it right. So these two are not disjoint. Very few people got those ones wrong. These ones are disjoint, and almost everybody got them right. You guys are doing quite well. Let me address E1 and E2. I thought I would trap more people with E1 and E2. E1 and E2 are not disjoint. Not disjoint is the correct answer, but they are something else. So E1 and E2, just like disjoint is something that happens between two sets. There's something different that can happen between two sets, and E1 and E2 are that something different. Does anyone know what that something different is? Yeah.
The union?
They're not. No, they're not. It's not the union. Yeah.
They're independent?
They're independent. So later on in the course, we're going to learn about independent, and E1 and E2 are independent events. And independent has a very specific definition we'll get to later. Sometimes people mix up disjoint and independent. Don't be like those people. So you guys, I think you guys got it very well. This kind of level of progress makes me think you're understanding quite well, and that's wonderful. Okay. If you're confused about these, maybe I'll post a quick video or something with like the solutions, but in the interest of time, let's move on to the next thing because you guys seem to all be getting this. And the next thing that I want to talk about is conditional probability. Conditional probability. So, and once again, if you're confused about the disjoint, it's totally okay. You can either post in the forum if you want more help, or I'll post some solutions if people ask me. So I'm moving quickly because most people have understood it. If you haven't understood it, it's okay. Please ask. Okay, so we're going to move on to conditional probability. Okay. And conditional probability is the next little thing with these little lines, and it's also related to independent. So when people say two things are independent, they're also talking something to do with conditional probability. This really is like, without conditional probability, probability is not very interesting. So this is, to me, this is like the secret sauce that makes you have some fun problems. And I wanted to start out with a fun little game we can play just to warm ourselves up on conditional probability. And here's the fun little game. Again, it's going to be in mathematized, but it's a fun game. So Professor Nika has a deck of 10 cards, ace through 10. Here are my 10 cards. This one you cannot get at Dollarama. These are the extra big cards that you got to pay the big bucks on Amazon for. I think it was like $6. So, okay, but I got ace through 10. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. I feel like I'm doing a magic trick. This is great. Okay, I'm going to shuffle the cards. A single card is dealt out, and a prize is given out if the card dealt is an ace. So we need somebody for this problem to make it a little more exciting and to add some stakes. We need somebody to be the potential prize recipient. And like I said, I have this free coffee card. There'll be a different free coffee card for the disjoint thing, but for this game, we're going to have a free coffee. Who would like a chance to win a free coffee? Let's pick someone here in the front row, because it's easy. So you're going to potentially win this free coffee. So I'm going to shuffle these cards. I'm very stingy, though. I'm not certainly going to give you the free coffee. I'm only going to give you the free coffee if you get the ace. All right? So here we go. This is your card. Please do not look at the card. No cheating. You keep them honest. Make sure they don't peek. So if they have the ace, I will give them the free coffee card. The probability of winning is 1 out of 10. There's 10 cards, sample space, ace through 10. 10 cards, 10 things in the sample space. 1 card on the table, if it's the ace, they win. So the event of them winning is that is the ace. That's an event with 1 element in it. So it's a 1 out of 10 chance to win. Okay, but now this is the exciting part. So that's probability like we've done it so far. But now is the new part. I'm going to reveal a card to everybody. Okay, here we go. The card being revealed is a 4. Question for you. What happens? Your options are the probability of winning did not change, the probability of winning went down, or the probability of winning went up. And if you can answer, can you also answer why and by how much? So I'll let you think about it. It's open now. Take 1 minute and decide what happened. It's similar. They're both about conditional probability. Yes. All right. There's like 20 seconds left. In the interest of time, I do want to get your guesses. So put in what you think. Can probabilities change or not? Okay. Time is up. Let us see what people think. Reveal counts. Oh, very even split. Half the class thinks the probability went up. Half the class, little under half, thinks it did not change. It's very tempting to think it didn't change, right? Because we're asking you in a math class, please calculate something. You would think that that answer can't change, right? But the correct answer, of course, is that the probability went up. The probability went up. I claim the probability is now, with what we know now, the probability is 1 out of 9. It's 1 out of 9. Since there's only 1 minute left in the class, we're going to leave the discussion of why is the probability now 1 out of 9 until Friday's class. But the most exciting thing we have to do is figure out did they win the card. So why don't you flip it over, and if it's an ace, you get a free coffee.
It's an ace.
Okay. We'll try again next class. Maybe we'll have a new winner on Friday. All right.